Okay, so how do we draw the absolute value of a function? We looked at simple ones earlier, you'll remember, just the basic absolute value of x. But what if we want to find the absolute value of any function? Okay, y equals absolute value of function x. As I say, we talked about this before. That's when we've got symmetry in the x-axis. Well, let's see what happens. In other words, what I'm trying to say there is we're going to reflect the bit of the original function that is negative, so the bit that's below the axis, we reflect it above. So there's our crazy random graph from before. If I wanted to do absolute value, the bit that's below, I've now got it, and I'm going to flip it above. So that would be y equals the absolute value of function x. Function absolute value of x now would have some sort of symmetry in the y-axis. So the bit that's in the positive, we reflect over. So let's draw this one again. Now this time, the bit on the left goes away, but we don't reflect that because we're substituting into the function, and because we're substituting absolute value of x in, we can never substitute in these negative numbers. So when I put -2 in, it first goes into the absolute value function, so I get the same answer as +2. So whatever's on the right-hand side reflects over on the left-hand side. So that will be function absolute value of x. Okay, what about absolute value of y is equal to function x? Okay, this also has symmetry in the x-axis. Reflect the part of the original function where the function was positive in the x-axis. Alright, so there's our original graph. Once again, the bit that's below has disappeared, but this time it doesn't reappear. The bit above reflects below. Because what we're saying is the absolute value of y is equal to function x. And I suppose that's the same as saying function x would be plus or minus y. So we get a reflection that way. Well, what the heck, let's absolute value both of them. So absolute value of y is equal to function absolute value of x. We could do it through a combination of the second and the third one. If I did y equals function absolute value first, or function absolute value of x first, and then do the absolute value of y of my new one. So it's going to have symmetry in both the x and the y axis. So it's the first quadrant basically will get reflected into all four quadrants. That'll be the overall effect of it. So here's random graph. First quadrant is the only thing that's left, and it gets reflected into all of them. So that would be absolute value of y equals function absolute value of x. Now, I might be getting a bit carried away now. I'm not sure we'll have this many combinations, but what the heck, let's keep going. Y equals the absolute value of function absolute value of x. So this one, I could do function absolute value of x first, and then do the absolute value of that one. So what we should end up seeing is some sort of symmetry in the y-axis and reflection in the x-axis. Okay? So basically, reflect the part of the original function where x is positive in the y-axis, then reflect that result. So here we go. Whoop. There's function absolute value x. Right? So we've gone from that to function absolute value x. But remember, I said we wanted y equals the absolute value of function absolute value x. So now, what do we do for absolute value? Well, whatever's below reflects above. So that would be y equals the absolute value of function absolute value of x. Did I keep going, or have I stopped being crazy? Oh no, I keep going. Okay. Absolute value of y is equal to the absolute value of function x. That would be a combination of the first one and the third one, wouldn't it? Okay. Again, we're going to have some sort of symmetry in the x-axis and reflection in the x-axis as well. The effect we should see, we end up reflecting that part of the original function where the original function is negative. We would reflect that in the x-axis, and then that result gets reflected again. So here we go. So first of all, I'll do absolute value of function x. So that was what we saw when we did that one. But we want absolute value of y is equal to function absolute value of x. So that gets reflected. Oh, now we can get some good graphs. So there's absolute value of y is equal to absolute value of function x. Now, I don't know that the exercise we're about to do goes as crazy as that. But, I mean, you can get all sorts of wonderful graphs by just applying absolute value to it. The other interesting one to look at is square root. So the graph of the square root of a function. Things to watch out for that. Well, we know you can only find the square root of a positive number. So all the negatives will disappear. And we also know, because we're talking about the positive square root, so the answer will always be positive as well. Okay, so here's our graph. The first thing I know is I can only find the square root of the negative number. So that bit's going to go away. So really, that's the graph I'm working on now. I want to find the square root of that graph. Similar to what we saw yesterday when we were squaring, we were squaring, the stationary points stayed at the same x values. Well, the same happens when you're square rooting. The y value will change unless it happens to be 1. But at that x value, you'll still have your stationary points. So, well, there's only one stationary point there. Stationary point's another name for a turning point, I guess. There's a turning point. It's bigger than 1. So if I find the square root of a number bigger than 1, I should get something smaller. Well, not smaller than 1, but smaller than the original number. So it'll come down a bit. Okay. Now, the asymptotes, horizontal and oblique asymptotes may change. So again, similar to what we saw with yesterday with squaring. So, there we go. My horizontal asymptote at this stage is less than 1. Square root a number that's less than 1, it gets bigger. So it's risen up. Won't go bigger than 1, but it'll go bigger. Square root of a number will be smaller, so underneath the original curve, if the number's bigger than 1. So the new curve will go below the old curve. And if the number is smaller than 1, the reverse will happen. The new curve will go above the old curve. But again, that means 1 is a crucial value. Square root of 1 is 1. So at all those y values of 1, I'll plot those in. We know square root of 1 is 1. Those points will remain. Now the X-Intercepts are really interesting. Require close inspection, you'll see I've put there. Okay. Think about this. Y equals x to the power of a on b. I don't know whether you've even noticed this before or not. There's x to the power of a third, and there's x to the power of 2/3. Okay. So if a on b, if that fraction is less than 1, what you should see happening is the curve is concave down, and I'm talking in the first quadrant here, and at the origin, at the x-intercept I should say, you get a vertical tangent. Now over here on 2/3, that's what's called a cusp when it comes to a sharp point, but that's still an undefined sort of tangent there because of the nature of the curve. So you're either going to get a cusp, but a vertical tangent. Okay? And there's, well, x to the power of 3/3, of course, is x to the power of 1, so we get a straight line. 4/3, 5/3 and 6/3. So now that it's gone bigger than 1 the power, you'll notice instead of it being concave down like that, it's now concave up. So it goes concave up, and we end up with a horizontal tangent now instead of a vertical tangent if we were to draw it. So I don't know whether that's ever been pointed out to you, but there's 5/3 and obviously 6/3 is our parabola x squared. So in general, you can see things like this. If the original function was x to the power of 4, well, the square root of x to the power of 4 would be x squared, so you're expecting the parabola. And then y squared, we'll talk a bit more about that later, would actually reflect. X cubed, the square root would be 3/2. 3/2 is bigger than 1, so we end up with this concave up shape with a horizontal tangent. Notice the left-hand side disappeared because once we went square root, can't find the square root of a negative number. Disappeared. X squared. Well, square root of x squared is x. So we end up with a straight line, but it has a sharp point there. It's just like the absolute value graph, if you like. 5/3 was the original graph. Find the square root of 5/3 and you get, well, 2.5/3 if that's possible, but anyway, it's less than 1 is what I'm getting at. So the curve ends up going concave down instead of concave up. Let's look at ours. Now obviously I don't know the function here, so I can only guess. But they look pretty much like single roots, power of 1. Remember, the X-Intercepts behaves like the roots. So best I can do here is guess that each of these are just cutting it like a straight line. If I go back to the original graph, you can see that indeed it did. So if it's a single root, power of 1, when I find the square root of that, it's a power of a half. A half is less than 1. So I'm expecting a concave down shape with a vertical tangent. See if I can do that. We'll plot those x's. Yeah, well, I might have exaggerated the one on the right there, the vertical tangent, but I've got that sort of shape. And keeping in mind all the other things as well. So when the value is below 1, it's gone above the original curve, goes through 1, then below the original curve. It goes above the original curve, through 0, below the original curve, above the original curve, and I'm trying to get that vertical tangent. Not easy to do in PowerPoint, I've got to tell you, trying to do that. And there it is, in all its magnificent glory. Okay. Sometimes, instead of asking us to draw y equals square root of function x, they ask us to draw y squared equals function x. Essentially the same graph, but now you get plus or minus the square root. So all that does is reflects it in the x-axis. So if you have to do y squared equals a function, you draw y equals the square root of function x and then just reflect it over, and there's your picture. All right, so we just had a handful of questions there.